When designing a new service entry, especially in situations where the utility company provides conservative fault current values, selecting appropriate service switches and switchgear breakers with adequate interrupting capacity is crucial. Several manufacturers offer solutions exceeding 200 AIC at 480 volts. For service-rated switches, consider the Eaton EH series, which offers a 4000 amp rating with up to 250 AIC at 480 volts. Another option is the Siemens SW series, also with a 4000 amp rating and an interrupting capacity of up to 225 AIC at 480 volts. ABBT Max SV series provides a 4000 amp service switch solution with an interrupting capacity up to 250 AIC at 480 volts. If you prefer switchgear breakers for the application, several suitable options are available as well. The Square DQR series offers breakers up to 4000 amps with an interrupting capacity up to 250 AIC at 480 volts. Eaton EH series switchgear breakers, similar to the service switch counterparts, provide up to a 4000 amp rating with up to 250 AIC at 480 volts. The Siemens Centrum 3WL series offers switchgear breakers up to 4000 amps rated at 225 AIC at 480 volts. It is important to know several key considerations. Firstly, verify the actual available fault current through a comprehensive fault study. The infinite primary calculation method often employed by utility companies like Con Edison can be overly conservative. A fault study will provide a more accurate assessment of the available fault current at the service entrance, potentially allowing for the selection of less expensive and more readily available equipment. Secondly, consider using fuses rated at 300 AIC to supplement the switchgear or service switches. Fuses, especially current-limiting fuses, can provide an additional layer of protection and enhance the overall interrupting capacity of the system. Thirdly, explore options to reduce the available fault current at the service entrance. This can be achieved by installing current-limiting devices such as reactors or current-limiting fuses. Reactors introduce impedance into the circuit, which limits the fault current. Current-limiting fuses, when properly sized, can clear a fault very quickly and limit the let-through current. Fourthly, consult with the utility company to explore any other options they may have available. They may have additional data or suggestions that could help optimize the service design. It's worth reiterating that the use of the infinite primary calculation by the utility company is often an overly conservative approach. This can lead to oversizing of the service equipment, resulting in unnecessary costs and complexity. Obtaining a more accurate fault current calculation from a qualified engineer or through a detailed fault study is strongly recommended. This will allow you to select equipment that is appropriately sized for the actual fault current conditions, ensuring both safety and cost-effectiveness. In summary, when selecting service switches and switchgear breakers for applications requiring high interrupting capacity, several reliable options are available from manufacturers like Eaton, Siemens, AIC, and Square D. However, it's crucial to verify the actual available fault current through a fault study and to consider using supplementary protection devices or current limiting techniques to optimize the service design. Remember to consult with qualified engineers and the utility company to ensure a safe and cost-effective solution. A deeper dive into fault current calculations is essential. Fault current is the amount of electrical current that flows during a short circuit condition. The magnitude of the fault current depends on the voltage, the impedance of the power source, and the impedance of the circuit up to the point of the fault. The available fault current is the maximum current that a power system can deliver to a fault location. This value is critical for selecting electrical equipment, such as circuit breakers, fuses, and switches, that can safely interrupt the fault current. Calculating fault current involves several steps. Firstly, gather the necessary data. This includes the utility's available fault current at the primary side of the service transformer, the transformer's impedance, the length and size of conductors, and the impedance of other equipment in the circuit. Secondly, convert all impedances to a common base. This is usually done by selecting a base kilovolt ampere, kVAR, and a base voltage. Thirdly, calculate the total impedance of the circuit. This involves adding the impedances of all components in the circuit, including the utility source, the transformer, conductors, and other equipment. Fourthly, calculate the fault current. This is done using Ohm's law, which states that current equals voltage divided by impedance. The fault current is equal to the voltage divided by the total impedance. Different methods can be used to calculate fault current. The point-to-point method is a simplified method that can be used for quick calculations. However, it is less accurate than more sophisticated methods. The impedance method is a more accurate method that takes into account the impedance of all components in the circuit. Software programs are also available that can perform fault current calculations. These programs can handle complex circuits and provide detailed results. The infinite bus method is a simplified approach often used when the source impedance is much smaller than the impedance of the downstream circuit. In this case, the source is treated as having zero impedance, which simplifies the calculations. However, this method is typically only used for preliminary estimations, as it often overestimates the fault current. Understanding the factors that affect fault current is crucial for accurate calculations. The utility's available fault current is a major factor. The higher the utility's fault current, the higher the available fault current at the service entrance. The transformer's impedance also plays a significant role. A transformer with a lower impedance will allow more fault current to flow. The length and size of conductors also affect fault current. Longer conductors have higher impedance, which reduces the fault current. The impedance of other equipment in the circuit, such as motors and generators, can also affect fault current. After calculating the fault current, the next step is to select appropriate electrical equipment. Circuit breakers, fuses, and switches must be rated to interrupt the available fault current. The interrupting rating of the equipment must be greater than or equal to the calculated fault current. The interrupting rating is the maximum fault current that the equipment can safely interrupt without being damaged. It is important to select equipment with an adequate interrupting rating to ensure safety and prevent equipment failure. Several types of protective devices can be used to limit fault current. Current-limiting fuses are designed to quickly interrupt a fault and limit the let-through current. Reactors are inductive devices that add impedance to the circuit, which reduces the fault current. Surge arresters are used to protect equipment from voltage surges, which can occur during a fault. Ground fault circuit interrupters, GFCIs, are used to protect people from electric shock. They detect ground faults and quickly interrupt the circuit. Arc flash is a dangerous phenomenon that can occur during a fault. It is a type of electrical explosion that can cause severe burns and injuries. Arc flash hazards can be reduced by using arc-resistant equipment, implementing proper safety procedures, and wearing appropriate personal protective equipment (PPE). An arc flash study is an analysis that determines the potential arc flash hazards in an electrical system. The study calculates the incident energy and determines the required PPE. NFPA 70E is a standard that provides guidance on electrical safety in the workplace. It covers topics such as arc flash hazards, PPE, and safe work practices. IEE 1584 is a guide for performing arc flash calculations. It provides methods for calculating the incident energy and determining the arc flash protection boundary. Ongoing maintenance and testing are essential for ensuring the continued reliability and safety of electrical equipment. Regular inspections can identify potential problems before they lead to failures. Testing of circuit breakers, fuses, and switches can verify that they are operating properly. Proper maintenance and testing can help prevent electrical accidents and ensure the safety of workers. Finally, remember to consult with qualified engineers and electrical contractors when designing and installing electrical systems. They have the knowledge and experience to ensure that the system is safe and reliable. They can also help you select the appropriate equipment and implement proper safety procedures. Electrical safety is a critical concern, and it is essential to take all necessary precautions to prevent electrical accidents.